We are now moving on to decimals and related ideas. And question is, what does decimal mean? So think about that for a second. The word decimal, what does it mean?
Is that just part of a whole again, like your percentages and stuff?
Yeah, so that's one commonly used definition for it, but it turns out decimal is a little more broad than that. Decimal on its own just means based on 10. So since last quarter, we've been using decimals. So 10 is a decimal, 12 is a decimal number. Anything you write down with the digits that we use are decimal numbers, because it just means based on 10. So all that stuff we played with before with place value is super important. We're just going to extend it a little more. Along with decimals, we're going to be looking at ideas related to what are called rational numbers. Oops. And irrational numbers. So as far as rational number goes, we've already been working with rational numbers. Rational means ratio, and fractions are ratios. So we've been doing decimals since last quarter because we have a base 10 number system. Base 10 numbers or decimals. We've been dealing with fractions, and fractions are rational numbers because they can be written as a ratio. And what we're really jumping into this chapter is what are called decimal fractions. Is the correct term for them. And decimal fractions are just fractions with only tens in the denominator. So fractions with denominators only based on 10. And we're all very used to these decimal fractions that we've been playing with for a large portion of our lives. But when they were originally introduced a couple hundred years ago, they did not go over well. Think about it. So rational numbers, fractions, right? You get things like 1/2 and 1/3 and 1/7 and 1/20th and 1 over any number you want, and you can put any number in the numerator. So we have things like 20 over 43 if we want. So we have all this freedom in our denominator. And then all of a sudden, this idea was floated out there in the world that, well, what if instead of having denominators like 2 and 3 and 7 and 20, what if, like our whole numbers, our denominators were only based on 10? And you can imagine a lot of people like, well, what about thirds and sevenths and 20ths and halves? I need those, right? You can't take those away from me. So we've been playing with fractions and whole numbers a lot longer than we've been playing with these things called decimal fractions. And they did cause a stir when they were first introduced. They were introduced a couple of different times in a couple of different ways, and it was a while before they caught on. I would say like 100 years. So they're pretty new in our history of playing with numbers. So as far as decimal fractions goes, that means I can have things like 1/10 and 1/100th and 1,000th. And my denominators can only be based on 10, which means they can only be powers of 10. So 1/10 is 1/10 to the first, 1/100th is 1/10 to the second, 1/1000 is 1/10 to the third. So the idea was we just extend the place values that we had before to use fractional powers of 10. Or yeah, something like that. So let's look at this in a little more detail. Place value. So kids for a while have been getting used to their different places, their ones and their tens and their hundreds and their thousands. But you might notice when you hear kids reading and they're reading a book and maybe a date comes up in the book and maybe it's something like 1996 pops up, that what that number means to them isn't entirely clear. Some kids might read it as 1996. Some people might read it as 1996. Some kids might actually recognize it as 1996. There's lots of ways to look at that and read it in a written context. But the place value is super important, that's a 1000, right? Remember our expanded form? And that's a 900, 900s, literally. And then we have 9 tens, and we have 6 ones. So we're going to reinvestigate this expanded notation, but with decimals also. So the idea of decimals was to just keep going with the places. So we have our tenths and our hundredths. Just going to abbreviate them that way for a moment, and our thousandths. And to separate, to know when a digit meant one or the other, there were many ideas that were floated out there. But the one that survived is that we put this point right here, this thing we call the decimal point. That separates the fractional part from the whole number part. Right? So here's our whole number part of the number. And there. And this over here is our fractional part. And I guess I should be more clear about that. It's a proper fraction on this side. Remember we talked about proper fractions versus improper fractions. Again, our number system is based on 10, and all of these are powers of 10. So the ones, remember, is 10 to the 0 power. Our tens would be 10 to the first power. 100, 10 to the second power, 1000 is 10 to the third power. And similarly, going this way, instead of being this the 1/10th place, we could call it the 10 to the -1 place. Negative exponent means flip the base. 1/100th is a power of 10. It would be 10 to the -2, and 1000 would be 10 to the -3. And you have to excuse me for 1 second. I think I might have a call I have to deal with. Sorry. Okay. You can hear me, right? Still?
Yes.
Okay. Let's see. So we've got these positive powers for place value, and now we have a negative exponent, just means flip the base. So that's a good thing to know. So if I wanted to expand a mixed decimal number, like maybe 3.25. So that would be 3 ones and 2 tenths, which I could write like that, and 5 hundredths. Now I could also write it using exponential notation. So that would be 3 times 10 to the first, oops, I lied, 10 to the 0. Plus 2 times 10 to the -1, plus 5 times 10 to the -2. So we can still expand with decimals, and we can expand by either identifying the place value as, say, 1/10 or 100th, or we can identify it using exponents. Now, this is super important. When you look at our number system, and this messes some kids up, and some of you may or may not have had this problem when you were younger and dealing with decimals, the center of the way we write our numbers is not the decimal point. It is the ones position. Notice on the left of the ones position, we have our tens, and on the right, we have our tenths. We have our hundreds, and we have our hundredths. We have our thousands and thousands. And right in the middle is our ones position, 10 to the power 0. Okay, so that's the center of it all. And then we branch out on either side to bigger or smaller places than ones. And the reason I mention this is a lot of kids are used to their whole number things, right? Their ones, their tens, their hundreds. And on the other side, they want to be an exact mirror image of this, and they think the decimal is the mirror, in that they're looking for a once position. And there is no once position. There are ones, and you can increase to tens, or you can decrease your place to tenths. But the ones is the center of it all. And that's an important thing to know when we're playing with decimals. Ones are in the middle. And we branch out on each side to bigger whole numbers and smaller fractional numbers. Another thing. Decimal slang. So we're going to try really hard, and I'm going to have to try really hard too, to not speak slang with decimals. Okay, so here's an example of slang. When I read that, I often say 3.25. That right there is slang. That's not the proper way, the correct way to read decimals. The correct way is to identify the place value. So this is my tenths, that's my hundredths. So the correct way to read this is 3 and 25 hundredths. Three and 25 hundredths. 3 and 25 hundredths. Okay? Correct way is to identify the place value. It's a little different than expanding it, but that's the correct way to read a decimal. And it's something we have to really think about and practice because we are so used to the slang version of these. So identify place value. It's supposed to be a P. And so I just want you to, every time you see a decimal from now on, if you think to yourself, blah, 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 point, whatever, don't say point. Don't do this. Train yourself to try and read them properly. And I'm going to slip all the time because I use slang most of the time, except when I'm teaching this part of the class, and I try not to use the slang. And we really need to do that to help try to reinforce to the people that we're teaching what these numbers really mean. And reading it properly helps do that. Cool thing is reading properly also shows you how to convert a decimal to a fraction. And so the trick is to just read it properly by identifying the place value. Oops, letter, well, go with it. So for example, just real easy ones, 0.6 is slang. We're going to try not to say that anymore. Instead, we're going to look at that and say, oh, that's the tenths position. This is 6/10. Or quite mathematically, literally 6/10. And then we can reduce it if we want. So sometimes these reduce, sometimes they don't. So 6/10 reduces because I can divide top and bottom by 2, which is the greatest common divisor of these two numbers. And so it's also 3/5. And if we ask our calculator what's 3/5, it's going to say, hey, it's 6/10. Another example, slang, 0.17 or 0.17, right? The correct way to read this is 17 hundredths. Or mathematically, 17 hundredths. Now this one doesn't reduce, it's just 17 out of 100. Okay, so the decimal and the fraction reduced are the same thing. So slang would be 0.18, which we're going to try not to say anymore. Instead, we're going to read it with the place value. So I see 128, and that's tenths, hundredths, thousandths. So the correct way to read that, 128 thousandths. Or in fraction form, instead of words, 128 thousandths. And again, sometimes these reduce, sometimes they don't. So we could reduce that if we wanted to. And we could reduce it by either finding the greatest common divisor of each of these or noticing convenient divisors, like 2 goes in the top and bottom. And so I usually go for convenient divisors rather than finding the greatest common factor immediately, but both methods work. So half of 128 is what, 64 over 500, and they're still even, right? So we just keep working that pattern. Convenient divisors. Half of 64 is 32, half of 500 is 250. Oh my gosh, they're still even. When will this ever end? Someday, eventually, it has to. 16 out of 125. And 16 is even, 125 is not. Let's see, so 2 doesn't work anymore. Doesn't look like 3 is going to work. 5 doesn't work top and bottom. 5 squared is 25, which is bigger than 16, so I'm done looking. This is reduced. Remember, we have tricks to tell when we're done looking. The last thing to check was, does 16 go into 125? I don't know. I would have to check by actually doing long division or with a calculator, but I'm 99% sure it does not. So that would be the reduced answer there. So again, what's the important thing here? It's important to read decimals for a lot of reasons. One, it helps the people who are teaching decimals understand better what they are. And saying 0.128 has no meaning. It just says, hey, I see a point, I see a 1, I see a 2, I see an 8. But it doesn't tell us anything about what 0.128 means. Okay. And then the other thing is, it gives us a better understanding about how to convert to fractions if we need to. So that's useful too. Decimal comparisons. Decimal comparisons are like whole number comparisons. We compare place values. So if I look at, let's say, compare these two right here. Now, if we just talk about 0.4 and 0.125, that can give kids some misleading views. Like the 125 is 125 maybe, and 125 is bigger than 4. But when we do those comparisons, we have to compare pretty much all the place values. And I can see that in the largest place value, which is in this case the tenths, right? We're comparing a 4 versus a 1, and 4 is definitely bigger than 1, so it really doesn't matter what happens after that, right? So we look at the first place where they deviate in place value. So looking at these two, 0.4 is greater than 0.125. Oh, I did slang, you caught me. 4 tenths is greater than 125 thousandths because we have more tenths in 4 tenths than we do in 125 thousandths. So comparing these two here, they don't have the same number of places, so it can be helpful to fill in any missing places. And then identify where they differ. And so they differ here. So that's the first place that's different, and this one has more thousands than that one does. So then that leads us to say, okay, 3,260, let's see, what do we have? Tenths, hundreds, thousandths, 10,000ths is greater than 3,257 10,000ths. So again, practice reading these properly. Anytime you find yourself thinking 0.3257, try to stop and say, okay, what place is that? All right, so this would be 3,257 thousandths. It's the correct way to read it. So really condition yourselves to do that. It's hard because we're conditioned to just read it the easy slang way, which isn't productive in learning what these things mean and working with them. Okay, so what's next? Decimal representations. So as far as representations of decimals, like how do we look at decimals, like model them? There's two main models. We can use a grid model, or we could use a number line model. So the grid model is basically base 10 blocks or some variation of them. So I'm going to look at my base 10 block toy in a minute. And the number line model is just pretty much identifying them on a number line. Doing that for smaller decimals is pretty easy, but once we throw more place values in there, it gets harder to draw and zoom in on them, and sometimes we can't see them on the same scale, which we came across a little bit when we were playing with fractions and zooming in on them. So let's consider, for example, if I wanted to look at, before we were looking at 0.4 versus 0.125, I really can't easily see tenths and thousandths on the same scale, right? Think about that for a second. If I draw out a number line and I put, let's say I put 0 here just for fun, and then 1, 2, 3, 4, 5. This could be 1/10 and 2/10 and 3/10 and 4/10 and 5/10. And then splitting up the tenths to get the hundredths place, right? I would have to put 10 marks in between here. So let's go in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 would be the last one. I think I got enough in there. So those red marks there would be my hundredths. Now I want to try and put 10 marks between each of those hundredths to represent thousandths. And so I can't do that on the same scale. It's not possible. I would have to have a super big screen and picture to make that happen. So we got to be careful trying to compare place values that are too distant, because this place value right here is 100 times smaller than that place value right there. Okay. So I can approximate where that is on the number line on the scale along with this one, but there's some decimals you could make up that you just can't show together. So for example, let's use green to plot this one. That one's pretty straightforward. It lives right there. Now here, I can show there's 0.1, and then the second red mark over would be 0.1, sorry, 1/10, and then the second red mark over would be 12 hundredths, and in between those two would be 125 thousandths. So let's do that one, and I guess we can go blue. So right in between these two right there in the middle is my 125 thousandths. And right, it lives in between this red mark, which is 12 hundredths, and the red mark next to it, which is 13 hundredths. Okay, so getting used to placing decimals is sometimes not trivial. You got to think about it and have the right scale drawn out. And so you'll see lots of worksheets and online activities that kids do where they have to try to put decimals in the right spot compared to each other. And sometimes when we play with multiple place values at the same time, like tenths versus tenths and hundredths, or tenths, hundredths, and thousandths, it's a bit of work to get things placed right. So that's the number line model. It's just a matter of having a correct scale drawn out and putting numbers in the right spot, which is a little easier than working with fractions. So that's one nice thing about decimals. The number line is a lot easier to work with in finding where numbers are. For the grid model, we have to identify what one whole means, and that's up to us. So if you think about our base 10 blocks we've played with, they have this little cube or square, and then there's a long piece, and that could go in any direction we want. And then we have this other bigger square type piece. And a lot of classrooms will have physical versions of these, where this is a unit cube here. So this is often called the unit. And it's just a small cube. This one right here is often referred to as a long, right? Because it's longer than the unit. And it's actually like, you know, just a small, I didn't make those the same size, oops. And this is somewhat important, that when I'm drawing these, I want to make it look like 10 of these units make a long, and 10 of these longs make what we call a flat here. So we have the unit, we have the long, we have the flat, and there are, in the three-dimensional versions that we play with in the classroom, there's actually a big cube made up of 10 flats, but I'm not going to draw that here. And any of these could be a whole. We could say that's one whole. We could say that's one whole. So in the past, when we were working with whole numbers, right, the unit was a whole, the longs were tens, and the flats were hundreds. So now we're just going to redo that, and we could do something, let this flat be one whole. Well, that means this long would be 1/10. And this unit here would then be 1/100th of the whole thing. And sometimes when we're modeling with these base 10 blocks, somebody might pick for an important reason that the long is going to be the 1. So that's another possibility. So then with these, I could illustrate, for example, 2 and 13 hundredths. So to do that, I would have to show 2 flats, because that's what I'm saying a whole is. And then I only need 1/10, which I can draw in that direction. That was a nice rectangle, isn't it? And then 1, 2, 3 units. So knowing that that's one whole, this would be the graphical interpretation of 2 and 13 hundredths. Now it could be we want to show thousandths, in which case we'd have to redo our key. So I'm going to go over to the toy for this. Math Learning Center. Number pieces. Okay, so I need a link to that. I thought I put it in there. So let's put it in there now. I'll put it in the chat for anybody that wants to play with it with me. All right, so this is just the generic version of it, but it's got that nice share option, so we can share these finished ones with each other. Right there. And remember from last term, or if you didn't take it last term, if you're new with me, then there are two different versions down here of the coloring scheme. So this one has them all in yellow, and then there's this other one that has them colorized. And usually when I'm playing around with place value, I like the colorized version, so I can clearly see the difference when I merge them and not. So for example, zoom out just a touch, there we go. So that number I was just playing with, if this is a whole, I now have 2 wholes, and then this would be 1/10 and 3 ones. So 1, or 3, sorry, not ones anymore, they are now hundredths in this scheme. So here I'm trying to illustrate, let's get the pen out, 2 and 13 hundredths. That's what I'm trying to show there with these toys. The cool thing about this version is if you get a whole bunch of these together, so let's get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I have 10 tenths, which is what I'm interpreting these now, right now, what can I trade them in for? Well, 10 tenths can be traded in for one whole. So then I can group those by circling them and then say, I think it's this button, join them. And because I'm in the colorized version, it says, oh, 10 of the greens make 1 of the reds, which is kind of cute. So when I merge them together, if I see them as greens, then they're not a whole, they're 10 tenths. And I can also split them. So if I select that, and then the bottom icon here is break it up, notice it makes them green again. And if I grab, they're separated again. So this is a nice feature of that colorized version. And it works similarly in the yellow version, but because I can change the colors of these if I want. But I do like the whole color change automatically when I merge them or split them. It's kind of nice. So it has some benefits from playing around. We'll use that more when we're adding and subtracting, multiplying and dividing. All right, let's make a new one here. I'll just clear this one. Reset. Yes, I'll start over. Okay, so I'm just going to add a note here. This time I'm going to let flat is going to now be 1/10. And pull that up a little. Making the flat 1/10 allows me to express other numbers. So for example, if I needed to illustrate $125 thousandths, I can now do that.
Hey, Gary, I'm sorry to interrupt. Do you mind? I need to step away for like 15 minutes. Is that okay? I'll be right back.
Okay.
Thank you.
Yep. Bye-bye. So if a flat is a tenth, this is the 1/10 here. And then I have 2 hundredths, so this must be 100th, and I can have 2 of them. And then the smaller piece is then going to be 1,000th, so I can put in 5 of those. So this would be an illustration if a flat is 1/10 of 125 thousandths. Now I'm going to put that in expanded form too. So in expanded form, I have 1/10 and I have 2 hundredths and I have 5 1,000ths. There we go. So I can't get pretty fractions here, but I can type it out at least like that. So that's one way to write the expanded form. And I can't do exponents, but I can try. I have to write this with my mouse, wish me luck.
So 1 times 10 to the negative 1 would be my tenths. And 2 times 10 to the negative 2 is another way to write my hundredths. And 5 times 10 to the negative 3 would be my thousandths. So that's another version of the expanded form of this number I'm trying to illustrate here. All right, so let's see, we've looked at decimal fractions, mixed decimal numbers, expanding them, reading properly. We next need to talk about rational numbers.